Welcome to the lesson on species balance equation. This lesson is part of mass transfer, which is being taken up as part of the NPTEL-MOC on transport phenomena in materials. So the objectives of this lesson are as follows. Derive a generalized species balance equation using control volume approach. Show equivalence with continuity equation. Introduce diffusional flux using a constitutive relation, and simplify to arrive at Fick's law of diffusion. So as you can see that we don't introduce Fick's law directly from nowhere, but we want to take up the ideas that we have developed in the earlier sections. For example, in the fluid flow, where the mass balance has been introduced as a continuity equation, and we want to use the same ideas and develop the species balance equation and see the equality between the two approaches, and use the constitutive relationship essentially to bring about how the Fick's law is being interpreted. So there are some symbols that we need to make this lesson, and these are as follows. Earlier we have already discussed the difference between concentration and composition and the various units that one could use. So here we have the variable that is being used for the species balance is basically the concentration of the species I, and you could also call it as a density of species I, because the units that we take are kilograms per unit volume. Ideally we should actually use the variable rho I, because that would remind us that it's actually having units kg per meter cube, but most of the books use Ci as in concentration of species I, and we will use the same symbol here also. The second symbol we need is ui, and we have put a vector on top to indicate that it's actually the velocity, and the subscript I shows that it's the velocity of the species I, which means that when we have 2 or 3 species in a particular domain, then it is not necessary that all the species are moving at the same velocity. And if they were at different velocities, then what did we mean by saying the velocity of the fluid? We will come to this discussion somewhere in the middle of this lesson. The total number of species in the system are n, and n can be 2, 3 or whatever number we choose. There are some reactions that we think are possible in the domain, which is why the species could be actually generated within a control volume. So the number of reactions we are denoting is by the symbol R. So here is some quantity which we have introduced in an earlier lesson already, the kappa ji qj. So this term we have introduced in the previous lesson. It is basically telling you the generation of the species I from the reaction J. So you can see that the subscripts of qj is coming here, and the kappa ji is coming as a coefficient of the stoichiometric equation that involves the species I, and together this is telling us what would be the rate of generation of species I per unit volume. And we have the definition of density, because we are talking about concentration of any species I as a Ci, then the sum of all the species must be equal to the mass, and therefore the density is now arriving at from this simple expression where rho is equal to sigma I is equal to 1 to n Ci, or alternately you could also write this way, rho I, okay, and I is equal to 1 to n. So both are equivalent. This actually looks more elegant because on either sides we have the concentration or of mass or mass density. Now the conservation of mass within each reaction requires a particular equation, and that equation, as we have seen earlier, is that it is sum of kappa ji is equal to 0, and this we have already done an illustration, and the jth reaction for which we are writing this expression, I is a species that is participating. In the jth reaction we have taken an example of woostite plus hydrogen giving iron and water vapor, and you can see that we converted the moles here to weights. So these are all basically in grams, and then we have a convention that what comes on the left hand side of the reaction are denoted with a minus symbol, and what comes on the right hand side are denoted with a plus symbol, so that the equation is indicating that if it is proceeding further at a rate q, then it means that iron is being produced, H2 is being produced, the wustite is being consumed, and hydrogen is consumed. So the consuming part is actually indicated with the minus sign, and from here itself we can immediately see that summation of kappa ji over the all the species for this reaction jth reaction is 0. Now this we need because we are going to use it in the derivation, so we are going to note it down and keep it with us. Now the rate of generation of species, we have already mentioned that it is kappa ji qj, and this is for the jth reaction. Okay, and we said that there are r number of reactions that are possible in the domain, and so therefore we can say that the total rate of generation of species I should be basically a sum of generation from all the reactions, which means that we should take a summation. So this is what comes out. So qi is basically, this is qi is the total rate of generation of the species I, and on the right hand side we have a summation, and this term for the jth reaction is already familiar to us. We just only sum it up for all the possible reactions. Okay, and if this was a rate per unit volume, okay, rate of generation of species I per unit volume, and the control volume approach we are taking for the derivation, and it has a volume dV, it implies that when we multiply the volume of the control volume with the rate of generation, we get basically the increase in the mass of the species I per unit time, and that is what we write by this equation. So we basically write integral of qi dv, integral qi dv. This is basically rate of increase of mass of species I in the control volume, and on the right hand side we basically expand it. Okay, so this is a slide I have taken from one of the lessons while deriving the continuity equation to talk about the convention for the flux. We write that if the flux is written as J, then it is always outward normal. Okay, so the elemental area is having an outward normal, which means that if we take j dot ds, which is basically the outward normal dot the j vector, the flux, then it should give you a quantity that is going out of the control volume. So that's why we say that j dot ds is basically the outward flux. Okay, so this is what we wanted to tell. This is outward. Okay, so if we want what is the total flux of any species that is coming into the control volume, naturally we will have to put a minus sign in front of that. So that's the reason why we bring this slide again here. So the flux of species into the control volume is indicated as ji. So as you can see, just a moment back we had only j here without any subscript. The reason is that it was taken at a time when we were only looking at uniform material, and now is the time we are actually looking at specific species for which we are going to look at the balance. So ji is the flux of species I across the phases of the control volume, and so naturally then j dot n is the outward flux of the species across the area ds, which means that when we integrate over all the surface area of the control volume, then we get the total outward flux, and with a minus sign in front we will get the total inward flux. So with this minus sign here, we say that then it is basically inward flux, and we say it is total because it is over the integration of the control volume. All the cases are being used for this particular term. Okay, so what we are saying is that now we are going to look at a control volume that is fixed in the space and say how the rate of change of the mass of the species I in this control volume is going to be affected. Okay, and so what we want to say is that the rate of change of mass of species I in a control volume dV is then given by dou Ci by dou T into dV integral. Okay, now this is a volume integral, and as you can see that it is just rate of change of mass because this is already per unit volume and into the volume itself. So that is nothing but this term will have a units of kg per second. Okay, and we have taken the liberty to take this differentiation with respect to the time inside the integral, because the control volume is fixed in the space. So we did not have to go through the trouble of using the transport theorem to do anything here. You see, the volume is actually fixed in space, imaginary volume through which material is coming in or going out. So we now need to make a statement in plain English. What is the balance of mass for the species I? And what we say is as follows. We say that the rate of change of mass of species I in a control volume, which is then indicated with this term integral dou Ci by dou T dV, is equal to the total influx of species I through all the phases of CV, which is then indicated with this term minus integral Ji dot n ds, that is the integral of the flux over all the control volume phases, plus the total generation of species in the control volume, which is given by this integral of this Qi dV, which is expanded as integral sigma kappa Ji Qj dV. So what we are trying to say is, if there is any increase in the mass of any species, it must be because it has come through the phases or it has been generated inside. Okay, there are only two ways by which the mass of any species inside the control volume can actually increase. Okay, so now we write this statement in an equation form, and that appears like this. So whatever is increase of the mass in the control volume is equal to what has come inside from the phases plus what has been generated. And we see that the first integral is a volume integral because it's over dV, and the second integral is a surface integral, and third integral is again a volume integral. So we could actually put multiple of these integral signs, but we don't want to make it cumbersome and leave it just one integral sign. Okay, now we cannot proceed further unless we convert the surface integral to volume integral, because then we have all the integrations over the same control volume. So we can make the same kind of a simplification as we did in the lessons earlier in the heat transfer as well as in the fluid flow. So now we basically require Gauss theorem to convert the surface integral to volume integral, and we have already seen that here whenever you have a dot product, basically you can take that as basically the divergence of that same quantity, and then you have the integration possible. Okay, so this is the conversion that we are going to do, and when we do that, then it is coming out to be in this form. Now all these three integrals are over the same control volume fixed in the space, and which means that we can actually assume that the equation is holding also for the integrands. So we take only the integrands. So this term we have here, this term we have here with a minus sign, and this term we have here. So we take these three terms and then use the equation to write the mass balance as follows. So this is basically the strong form or the differential form, saying that the increase of this mass of the species I in a control volume is nothing but the total influx of the species I plus the total generation of species I due to all the R reactions that are taking place in that particular control volume. Okay, so we have finally actually arrived at the balance of mass. So at this point we can say that the species balance equation is derived. However, it is not in a form that we recognize in many of the books, so we need to basically look further of what we can actually modify this to be, so that we see the equations in a form that are actually available in most of the metallurgical textbooks. So the flux is usually expressed in terms of velocity. This is something that you could find in as basic a book on physics like as in Feynman lecture series, for example, where we always write flux as concentration times velocity. And you can see that does make sense, because the flux is generally given as kg per meter square per second, the concentration is given as kg per meter cube, and velocity is given with meter per second. So you could see that from the units it does make sense. It actually tells you that across a phase you have basically velocity of the species multiplied by the concentration, giving you the flux itself. Now we have the balance equation that we have just now derived, and there we had a quantity Ji. So basically we would like to use this expression to substitute there. So that's what we do now, and we now have slightly different species balance equation where we do not have the flux, we have actually the velocities. It's quite convenient because we want to reduce the number of quantities to what we directly know about, and we want to actually make it look more and more familiar with what equations we have derived in earlier units in this particular course. So we now have a slightly different form. So we will now go further and see what more we can change in this particular equation. Okay, and one question that arises here is, if this was the mass balance equation and it conveys the same sense as mass balance as the continuity equation, but doesn't it look the same? And of course the reason is this is written for a particular species and the continuity equation is written for the homogeneous uniform material. Now can we actually draw a parallel between the two? Is it possible for us to arrive at the continuity equation starting from here? So naturally yes, and that's what we can illustrate in a moment. So what we do is that to get the total mass in a control volume, we have to sum up the masses of all the species that are in the control volume. So what we do is that this equation we have written, we sum it up for all the species, and we know that there are n species that are there. So one equation which we have for the ith species, we simply sum it up. So we can see that here is the summation of all the species from I to n, here and here. So from here to here we basically have done only the summation. But while doing the summation, we do have some relationships that we know which we can start to use to simplify. Okay, and on the process of simplification, we also need to use what we have derived with respect to the kappa, and we already saw that the summation of kappa would actually have a 0, but then here the kappa is multiplied with q. Now if you look at this term, this is basically n star r terms. Okay, and if you expand, then you can actually collect all the terms that come with the coefficient qj and then sum it up. So which means that we can actually take qj as a common and swap the two summations and rewrite the expression like this. Okay, this is a acceptable one, because what we are doing from here to here, this particular change is basically that we are actually taking the qj as common. Okay, nothing more than that. Everything else is same. So this is basically taking the q as common, and we will see that some more things can be simplified. So from the definition of density, we already saw that the first term is basically nothing but rho. So that's what we substitute here, and from the mass balance within an equation, after we made the stoichiometric equation and chose the convention of kappa to be negative on the left hand side and positive on the right hand side, we ensured that the mass balance has to be there, and that gave that this term summation is 0. So which means that this entire thing will have to be dropped. Okay, that means it has to be 0. Now which means that we can actually simplify the equation to be like this. On the left hand side we basically have sigma ci is nothing but rho, so that's what we use, and the right hand side the term here which remains the same. So this is slightly simpler. So this looks quite close to how the continuity equation would look like, but we still have to go a bit more, because we have here the velocity of the species I, and in the continuity equation we have u, which is basically the velocity of the material, and we have to find a way by which we can reconcile these two quantities. So what we mean by the velocity when we were doing the derivation in the fluid flow is something that we need to define with respect to the velocities of the individual species. So that's what we would do here. So consider that at the microscopic scale, the species are basically molecules or atoms. They're all moving in some direction, and so if you look at the velocity of the center of mass, you can see from the way we have drawn naturally that the velocity is going from the left to the right, and the center of the mass is indicated here with respect to this square in green. So as the atoms are moving around, you notice that the center of the mass is actually moving in a direction, and you can call this as the velocity, which is what we actually mean by the velocity of this material. And this doesn't actually prevent some of the particles or some of the atoms moving in different directions. It's only the center of the mass that we are concerned while defining u. So it means that the u for this particular two fellows will be different, but for the rest they are actually going to be very close to the velocity of the center of the mass. So that is something that is a measure of an averaging of the atoms, so which means that it is a quantity that is useful at a system scale, and naturally that's why we are using it in the fluid flow. So we now define the velocity of the center of mass formally as follows. We define it as a barycentric velocity. That means that we are actually using the mass concentration to average the velocities of all species to define what is the velocity of the center of the mass. So the velocity of each species is ui, and the concentration of each species is Ci. So if we average using the concentrations, then we get an average quantity which is the barycentric velocity, and that is basically what we refer as velocity of the center of the mass. Naturally, you can actually choose any other quantity to be the averaging. You can take not just mass concentration, you can also take mole concentration for averaging and anything else, and those quantities will not directly lead to us in this particular derivation towards continuity equation. So that's why we pick the barycentric velocity as our definition, and we already know that rho is equal to sigma Ci, so the denominator actually has rho, and so the barycentric velocity has a simpler expression, and so this is a formal definition. So this is what connects the ui of a species and u of the entire material. So you can see that the ui and u are connected through the averaging that is done as the velocity of the center of the mass. Okay, so now that we have defined this quantity, we can go and substitute this in the mass balance equation that we have derived. Okay, and that equation is here. So for this term we actually substitute the equation that we have just now introduced, namely the barycentric or the center of mass is moving, barycentric velocity or the center of the mass is moving at a velocity u, which is given by this expression. When we substitute, we get a simplified expression on the right hand side, nothing but rho u itself. Now this is something that we have already come across. This actually is a continuity equation, and we can actually take it to the left hand side, and there is a form that we have always derived. And when we expand this term alone and combine with respect to the partial derivative with respect to time and introduce what is called the material derivative, then we have an alternate form of the continuity equation, which is also familiar to us from our previous lessons. And in case the fluid or the material which we are having in the domain is a incompressible fluid, then we define that as basically continuity equation having the divergence of velocities as 0. So all those things are actually now making sense, because the concept of mass balance is quite embedded in the idea of macroscopic as well as microscopic pictures with respect to the mass balance. The velocity of species relative to the center of the mass is something that we have to pay attention. So this is something that we are going to introduce in a moment. The total flux of species I is given as Ji is equal to Ciui, and the velocity of species I relative to the center of the mass will then be Ui star. Okay, so this quantity we are just introducing now, Ui star. Ui star is basically velocity of species I relative to the center of the mass, naturally, because velocity of the center of the mass is u. Okay, so whatever is the difference, which means that if all the species were to be moving along with the center of the mass, then you basically have ui star as 0, and sometimes it is not so. Okay, and the reason why it is not so is something that we are actually going to use while coming up with the constitutive relationship. So the velocity of the center of the mass is basically what we refer to as advection, and it is due to the mechanical forces. That is the same reason as why the fluid will actually flow, namely the pressure gradients. Velocity of center of mass is basically advection, and this is due to the mechanical forces that are acting at a system scale. So we have already seen that in fluid flow it is a deviatoric stress that leads to the flow, and pressure gradients, gravitational body force, etc., all lead to the velocity. And so it's at that scale that this quantity is actually being influenced. However, at a micro scale, why would a species have a different velocity? And we then propose that it must be due to chemical forces. An atom is going away from the center of the mass because it is seeking a particular neighborhood which makes it go to a lower energy level. So at atomistic levels, it is the chemical forces that are responsible, and therefore we actually need to define a quantity called diffusional flux. So it is not the same as total flux. Diffusional flux as opposed to total flux. Okay, and total flux we have already used a symbol J, so therefore we need to pick a new symbol, and that is basically Ji star. Okay, so we say that Ji star is the diffusional flux of species I defined using the velocity of species relative to the center of the mass. So basically, instead of ui, you say ui star, which is nothing but ui minus u. And if there are n diffusional fluxes in a system, because there are n species, then there is some conclusion that we can make. When we sum up all the fluxes, then on the left hand side we have seen the sum up, and on the right hand side you see that these two terms, when you sum it up, they actually cancel, because the definition of u already involves the summation of ci and ui. So it means that we now have a constraint on the number of diffusional fluxes of n species, with a condition that the summation has to be 0, which means that if there are n species in a system, then there are only n minus 1 diffusional fluxes that are independent. Okay, the nth equation is basically completely defined because of this particular condition that is coming up. So which means that the way we have defined the barycentric velocity, or the velocity of the center of the mass, is ingrained in the definition of the diffusional flux, and also is giving us the concept that there are n minus 1 diffusional fluxes that are independent. Now let us look at the solid balance and introduce the diffusional flux into that. So the equation that we used for solid balance is written here as it is, but we want to now substitute in the terms that are given here the new quantity that we brought about, basically the diffusional flux. So we have basically taken the diffusional flux to the right hand side, and you can see that it is coming as a sum up. Okay, so naturally we can see that Ji plus Ciu is nothing but Ci ui. Okay, so we basically have used the definition of the diffusional flux into the term Ci ui, and that we are substituting into the species balance equation for a species I. Okay, and this will basically make us have two terms on the right hand side. The first term that is going with the divergence, and what we take is one of the terms, we take it to the left hand side. So this term we take it to the left hand side, this term, and then the minus sign here make the term go to the left hand side as a positive sign here. So basically we have seen that the form of the equation is coming out to be something that is familiar to us. We have seen these kind of 4-part equations earlier, and our objective is to make the generalized solute balance equation to look very much similar to other balance equations that we have derived in this particular subject. So the generalized solute balance equation looks like this. Okay, and it has a very nice form, and we can see that this has all the terms which can be actually named in the same way as we have done it for the Navier-Stokes equation. The first term is basically the transient term, and the second term is basically the advection term. The third term, which is on the right hand side of the first term, is the diffusion term, and very aptly the definition of the diffusional flux is actually going in to give you the diffusion term. And the fourth term is the generation term, which is basically due to the reactions the species is being generated in a control volume, and that's the last term. So you can see that the generalized solute balance equation now here looks very complete, and this is something that is really useful for us. Now, why did we even bother to define the diffusional flux? we have not got much more ahead, because we still do not know what is this. So we have noticed in the earlier derivations in the fluid flow as well as in heat transfer that at this stage we introduce a constitutive equation so that we can expand this term. Okay, so we are going to do the same thing. So why did we define the diffusional flux? The reason is that in general stuff flows down the gradient of appropriate potential, and we see that in the case of fluid flow also down the gravitational potential is how the mass would actually follow. And here we would like to say also that the heat would flow down the gradient of temperature, which means temperature is the potential for the heat flow. So here also we see that if we were to think of what is the potential down the gradient of which material of species I would like to flow, and that is the constitutive equation that we want to propose. Okay, so we want to come up with that kind of a term, and we basically come up by looking at what is happening. So this is how all the species are moving, and we have looked at what is the definition of the velocity of the center of mass. It is actually going from left to right. The center of mass is indicated with the green box, and this is what we meant by advection or macroscopic flow. And the reason why it happens is because of Newton's law of motion. We have already derived these things earlier. Now if couple of these species are actually moving in different directions, that is because they are actually trying to find a company or the surroundings which are actually more energetically favorable. And even when a couple of species are moving in other directions, the velocity of the center of mass can still be defined, and in this case you can already see that it is still going in the right side direction as given by the arrow. So why would these some species move in a different direction at the atomic scale? And we say that is because the system is actually trying to evolve towards chemical equilibrium. The atoms or species are moving in a direction so that they actually find locations where the chemical potential is having no more gradient. The Gibbs energy is at a minimum. Okay, so if that was actually our reason, then we can actually propose a constitutive equation as follows. We say that a species moves relative to the center of the mass of all species because the gradient of its chemical potential. Okay, and which means that ui star is due to the gradient in the chemical potential, and this is now our proposed constitutive relationship. Okay, just like we said that heat flux is down the temperature gradient, we are basically saying something similar here, saying that the velocity of the species I, diffusional velocity of the species I, is down, minus sign is saying down the chemical potential gradient. Now these quantities are related with a coefficient m, and that coefficient is basically what is called as mobility tensor. And why do we want to call it as a tensor? So the left hand side is the ui star, which is the basically a vector. Okay, it's a diffusional velocity of species I. On the right hand side, mu, chemical potential, is basically a scalar, and mu I means chemical potential of species I, and gradient of a scalar is a vector. So on the right hand side, nabla mu I is basically, this entire thing is basically a vector. Okay, and the most general form of a constitutive equation to relate two vectors is actually through a tensor of order 2. Now we have not used subscripts like the way we did in earlier chapters. The reason is that we have already used the subscript here I for the species. I is for the species, and if we were to use one more subscript to indicate that's a velocity and two subscripts for indicating it as a tensor, the expression looks quite messy. So we just drop it, and we understand that if you have a vector and another vector, cause and effect, so you can say the cause is the gradient in the chemical potential and the effect is the diffusional velocity of species I, then they are related by a property which is basically a tensor of order 2. So mobility is therefore a property. Now what kind of components does mobility have, and what kind of a tensor is it? So just a moment, we have to just quickly talk about that. In crystals, M is a symmetric tensor, and we saw the reason for other properties to be symmetric was different. For example, in an earlier case, we have come across in the constitutive equation for heat flow, the thermal conductivity also coming up as a symmetric tensor, and there, like here, we are saying that it is thanks to the Onsager's reciprocal relationships. So the property tensor happens to be symmetric for a particular reason. We are not going into depth in that yet, and we want to only say that from the Neumann principle, we can say that if the domain happens to be fluid, that is a liquid or a gas, then that's isotropic, and therefore the property also should be isotropic, which means that the mobility m will have only one component. So which is quite a relief, because later on when we are deriving, we don't need to worry about how many numbers are there in front of us. It's just one number, which is a mobility. Now the chemical potential that we were writing the gradient of, we have to expand it so that eventually we come to use it with the concentrations. So here we expand the chemical potential in a standard form, as we would do it for deriving the meaning for the quantity called activity. We define activity through chemical potential in this manner, and this is a standard state that we happen to choose. And this activity is then written as a product of two quantities. The two quantities are basically the activity coefficient gamma and the mole fraction x. The capital X is used for mole fraction. All these are for the species I. Naturally, the gamma activity coefficient is a function of the mole fraction itself. We just want to take activity as a product of these, because it just allows us to talk about activity coefficient alone, and it simplifies some of the analysis later on. More about this in a thermodynamics course, but at this moment we just want to proceed further and substitute the expression here, which is basically A is equal to gamma I xi into here, and that gives us the expression here. And because it's a logarithm, we can actually expand it and we get two terms. Okay, and these two terms will be useful in doing the further derivation as we go along. Now we have to notice that this is basically constant, and so later on when we are going to do differentiation, we are going to basically drop it off. Okay, now gradient of chemical potential we need to expand. The chemical potential we have already written it down. Now we have to write the gradient. Now we choose a one-dimensional analysis for simplicity, and which means that gradient is interpreted as just the dou by dou x. Okay, that's quite bad, because life is not that simple, but nevertheless for illustration let us just take it as just one dimension. So what we now do is that we are transforming the variable. Instead of dou mu I by dou x, we write it as dou mu I by dou ci into dou c by dou x. Dou mu I by dou ci into dou ci by dou x. Okay, and we want to now change the variables, and the variables that we want to change are using the quantities that are listed here. Ci is concentration of species I, rho is density of the mixture or the material in the domain. Okay, and Wi is weight fraction of species, xi, capital Xi is mole fraction of species, mi is molar weight of species I, and m is the average molar mass. And we know already that Ci is the concentration, mass concentration of species I, and that can be related with the density rho and the weight fraction of species I, straightforward. And the mole fraction of species I can be related to the weight fraction by using these quantities m and mi, which are basically average molar mass and molar weight of species I. So which basically gives us a hint that you could actually relate Ci with xi, and the rest of the quantities are actually going to be dropped off because they are all constants. And over the distance that we are going to differentiate with respect to the distance, so over the distances that are very small, we don't have a reason to believe that the average molar mass would actually change much. Okay, and also we believe that the density is also remaining constant. So these are actually not true if you take some situations where phase transformations are happening, etc. But here we are looking at fairly homogeneous solution, and we are trying to look up the expression that we want to proceed further to realize from where the Fick's law comes, so we can make these assumptions. So remember that these assumptions are quite restrictive which is also going to impose those restrictions on the Fick's law. So let us see what does it mean. So we want to say that the logarithm of the concentration is somewhat like the logarithm of the mole fraction of species I, which means that this quantity that I was having in the equation, dou mu I by dou Ci is equal to 1 by Ci, dou mu I by dou ln Ci, which basically can be related to dou mu I by dou ln Xi. So you could already see the strategy. We saw that from mu we have got activity, from there you have got x, and so therefore we need to have somehow relationship between mu and x, and that's what we actually got here. Okay, so we are going to use this to derive further. Okay, so what we are going to do is as follows. So we have defined the diffusional flux as a Ci into ui star, and we have defined ui star as minus m into gradient of mu. That is the constitutive equation saying that the diffusion is down the chemical potential gradient, and the chemical potential gradient is expanded in terms of two quantities, which are basically the concentration gradient, which we leave it as it is, and the quantity which is basically dou mu I by dou Ci, which we saw that it can be related to the dou mu I by dou ln Xi, so that we have already seen this derivation. And in the mu I you are going to introduce the expanded form where RT ln gamma I and RT ln Xi are going to be used. So when we substitute all these things and expand, then we come to the following expression, basically Ji star is equal to minus mRT 1 plus dou ln gamma I by dou ln Xi into dou Ci by dou X. So the 1 here is coming because of this term. Okay, this is gone. Okay, this is gone because it's 0. Differentiation is going to give you 0. So this 1 is because of this term, and this term is here. Okay, so we are not simplifying it further, and RT has been taken common out. Okay, here, okay, and m is left as it is. So you can see that the derivation is quite straightforward, and this term is as it is kept here. Okay, as it is. Okay, so we see that now we are able to write the diffusional flux in terms of concentration gradient, which is something that we were actually looking forward to. Okay, so this is the constitutive equation that we are simplifying to. Okay, so our starting point was that diffusion of species is down the chemical potential gradient, and we are now saying that diffusion is related to the concentration gradient, and in the process of doing that we have introduced a constant d, and that d is now nothing but mRT into 1 plus dou ln gamma I by dou ln Xi. Okay, so this equation, by the way, is what is referred to as the Fick's law, Fick's first law. Okay, Fick's law of diffusion, where we say that the diffusion is down the concentration gradient. The proportionality constant is diffusivity d. Okay, and here the star is actually there, asterisk is here because it is there for us to remind that it is the diffusional flux and not the total flux. And so the English statement for the Fick's law of diffusion goes as diffusional flux of a species is down its concentration gradient. And we saw that the constant d was introduced, and it was actually a product of multiple things. So we saw that this d was nothing but all these quantities put together. The entire thing goes into the d. Okay, and so can we always say that d is always positive? So normally we write the Fick's law and say that d is positive, but it's not obvious here, because here we see that it's a combination of so many terms and it's not very clear whether it's always positive or not. What kind of values that this factor can take? This entire quantity, which is in red, is called the thermodynamic factor, and this factor incidentally can take a positive value, a 0, or a negative value, and depending on which value it takes, then the diffusion is going to actually be called with different prefixes. Now we want to do this analysis of dou ln gamma I by dou ln Xi, and for that we borrow some concepts from thermodynamics. So if you are not familiar with these equations, please go and refer to the solution thermodynamics chapters in a book like Gaskell, for example, or Robert Dehoff's book, and you will see these expressions that are there. Now these interaction parameter or the regular solution parameter, omega is a measure of how much the atoms like or dislike each other. So if the omega is negative, that means the atoms like each other, and if omega is positive, they don't like each other. And the activity coefficient gamma I is related to the omega and the atom fraction of the species in this particular manner, which is basically coming from the solution thermodynamics for regular solution with only one parameter omega. Now normally what we do is we plot activity as a plot against the atom fraction, and the atom fraction is going to vary from 0 to 1. Now when the atom fraction is varying from 0 to 1, the activity is actually also going to go from 0 to 1, and more importantly, in the limit of xi tends to 1, by definition activity is going to be taking a value 1, because that is the definition of the standard state we chose while writing the chemical potential mu. Okay, so how the plot would look like would actually tell you how this quantity would vary with respect to the x. Okay, so we remember that the gamma I is actually function of composition, and it's a basically ai by xi. It is not really the slope. Okay, it is just ai by xi. Okay, now an ideal solution is what is defined by taking a value of omega 0. Okay, ideal solution means omega is 0, so which naturally means that the entire thing on the right hand side is 0, which means that gamma is 1. So that is the conclusion, gamma is 1, which means that ai is just same as xi, which means that the plot is going to be a straight line. Activity as a function of mole fraction is going to be a straight line at 45 degrees going from 0 to 1. Okay, so the value here be 1. And what this implies is that dou ln gamma I by dou ln xi is equal to 0. Okay, this quantity, the thermodynamic factor is 0 because this quantity itself is 0. Gamma is 1. Okay. Now if you take a regular solution with the interaction parameter omega as a negative quantity, then you can see that the activity plot would be actually below the line which is given for the ideal solution. So there is a lowering of the activity at intermediate compositions. However, as the xi tends to 1, the activity will reach 1. So the curves will actually merge with that of the ideal towards the end of the plot. Okay, that is necessary because of the definition of the standard state. Okay, so if you have a regular solution with omega less than 0, it will give you that dou ln gamma I by dou ln xi as a positive quantity. Why is it so? The reason is that as xi tends towards 1, gamma I, which is actually less than 1, is actually having to increase to reach 1. Okay, so from a lower value it has to go to a higher value, reach 1, and therefore actually you see that dou ln gamma I by dou ln xi is greater than 0. It's a positive number. Okay, now if you take a regular solution with the interaction parameter that is greater than 0, the situation is different. Okay, you would see that the interaction parameter being positive means the curve is lying above that of the ideal solution, and that would give you the conclusion that dou ln gamma I by dou ln xi is actually negative. The reason why it's negative is that in this regime where you are supposed to go from 0 to 1 as xi tends to 1, you are supposed to have the gamma I which should actually come down. It should reach 1, so it has to come down, and that's why it actually has to be negative. Dou ln gamma is by dou ln xi is negative. The reason is that gamma I actually has to come down in magnitude from a higher value than 1 towards 1, so that when xi is tending towards 1, then you are reaching the standard state, giving activity value of 1 here. Okay, so we now can summarize all three behaviors as follows. The ideal solution has the interaction parameter 0, which will give you the thermodynamic factor 0. The regular solution, where the atoms seems to attract each other, would have the thermodynamic factor as positive. And if a regular solution is there where the atoms don't like each other, then you would see that the thermodynamic factor is negative. Now what does actually it convey? So in an ideal solution, which we also denote as Raoultian behavior, we say that because gamma is 1, we can say that this thermodynamic factor is 0, and whenever there is a mixing tendency or when the omega is actually negative, then you can have an Henrian behavior, that is the gamma is constant. You can have gamma as constant, and that would actually also give you the thermodynamic factor 0, but this is only at dilute alloys or dilute solutions usually, but for higher concentrations the Henrian behavior will not be there, and you would then come to a conclusion that the thermodynamic factor is positive. For a solution with demixing tendency, the interaction parameter is positive, and you can have an Henrian behavior even then for dilute alloys. It's possible where the gamma I is constant, and that will actually give you thermodynamic factor 0. But for intermediate compositions, definitely when omega is greater than 0, for intermediate compositions you have the thermodynamic factor negative. Now the thermodynamic factor going to negative value has some serious consequences. What we are actually trying to write is as follows here. So the constitutive equation is written in terms of d here, and that d is basically this factor. And what does it mean when you say the thermodynamic factor is positive or 0 or negative? Okay, so we see that it's a positive or 0 for situations of mixing or ideal solutions, and negative where there is a demixing tendency. Okay, so whenever you have the thermodynamic factor either 0 or positive, what happens is that this entire quantity will be then positive. Okay, this quantity is 0 or positive, 1 or positive, and which means that this entire thing will be basically positive. So the diffusivity is positive, okay, large and positive. So which means that you have a very standard situation that is taught in the textbooks, namely the Fick's law, telling that the diffusional flux is down the concentration gradient, and the coefficient is diffusivity, and diffusivity is positive. Okay, now we call it as a downhill diffusion because it is down the concentration gradients. Okay, now the other situation which we have come across is when the dou ln gamma I by dou ln xi, that is the thermodynamic factor, is negative. Now if it is slightly negative, like let us say minus 0.2 or something, it's okay because this entire factor will still be positive. But if it is negative and large, then you have a problem, because this quantity, this entire thing can be then negative, and which means that this quantity and this quantity multiplied will be negative, which means the diffusivity will have a negative value. Now that's quite strange, because normally we believe that the diffusivity should be positive quantity, but of course there we were assuming that it is for ideal solution, and here we have a situation where we have an alloy or solution that is demixing tendency is present, and the omega value is largely positive, so that is giving the thermodynamic factor as largely negative, and therefore the diffusion is up the concentration gradient. Okay, it is up the concentration gradient, and that's why this kind of diffusion is called uphill diffusion. Normally we tend to call this as a separate phenomena, and we call it as uphill diffusion phenomena. Actually it's not a different phenomena at all. It is the same as the downhill as far as the chemical potential is concerned. It's just that this thermodynamic factor happens to change sign, and therefore in terms of the concentration gradients it seems to be uphill. But please remember that this equation was derived with this particular expansion where the Ji star is always, we said that Ji star is always with respect to the minus gradient of mu I. So we always said that is down the chemical potential gradient. So there isn't actually anything called uphill diffusion when you consider the gradients of chemical potential. But in normal parlance we always tend to pick the concentration as a variable, and in terms of that variable maybe it is okay to say that the diffusion is uphill. Okay, and sometimes you may even have another strange situation that is possible, that is the thermodynamic factor is negative and small. Okay, how small? Let us say it is actually exactly -1. Then what would happen to this quantity? It goes to 0, which means that the diffusion suddenly is actually absent. Okay, there is a concentration gradient present, but the diffusion is absent. That is possible. It has been seen in some alloy systems in some composition or concentration regions, and that is because of this thermodynamic factor. So it's very important to know the origin of the thermodynamic factor and how does it play a role. Naturally, this is only a special case. For most of the situations, it's okay to assume that the thermodynamic factor is positive, and therefore the Fick's law is applicable. So the generalized solute balance equation that we have written earlier which we had in terms of the diffusional flux can now be written, assuming that the fixed law regime is applicable. We write that the diffusional flux of species I is related to the concentration gradients, and we can then substitute that quantity here, and we will write the equation as follows. Okay, so here is the generalized solute balance equation, where we see that all the variables are very familiar. So the variable that we are solving for is the Ci, which occurs in multiple terms, and the property is the diffusivity, and there's a reaction that is possible, and there's an advection that is possible. So this is in a format that we are quite familiar, okay, with respect to previous units of this particular course. So here is the equation, and we have modified this term on the right hand side with Laplacian, because we notice that the diffusivity, if it is taken as a constant across the locations, then we can take it out of the nabla symbol, and therefore we can write it like this. So here we basically have taken the d out. Okay, we can take a d out and have the nabla dot nabla, and that is giving you the Laplacian here. Okay, so this is the equation which we are familiar, and the transient term, the advection term, the diffusion term, and the source term. So the 4-part governing equations is now ready for us. Most of the time we actually don't use all these terms, and we drop some of them, and we will see the reasons for dropping, and respectively we can actually restrict the equation. So the second law of fixed diffusion is written by dropping these terms. We are saying that it is basically for a solid, therefore there is no advection, and it's for a system where there is no reaction, and therefore we drop those two terms, and we write the equation in this form, which is what is seen in many of the textbooks. Okay, so fixed second law is written as dou Ci by dou t is equal to d into dou square Ci by dou x square in 1D. If you wanted to write for multiple dimensions, you can do it by expanding the Laplacian operator here. Okay, so this equation is actually what is seen in many of the textbooks. As you can see that before arriving at this simple form, there is a lot of assumptions that were made and simplifications that were made, and many of them have to be kept in mind while trying to apply this equation to situations where those assumptions may not be actually reasonable. So our endeavor in the next few sessions would be to solve the generalized equation for the solute balance, or the fixed second law or the first law applied to various problems. And if you want to know more about this particular derivation, please look up the following references. The thermodynamic aspects of this derivation are all found in the book by Robert Dehoff. The ideas of the barycentric velocity, etc., were taken from the book by De Groot and Mazur, and the ideas of thermodynamic factor, etc., were taken from the book by Paul Schumann, Diffusion in Solids. So these three books are standard textbooks for these respective subjects, and I encourage you to explore more if you are interested in knowing more about how the generalized solute balance equation has come about.